All right, welcome to Chapter 7, where we are starting our discussion on chemical equilibrium, starting with the principles of chemical equilibrium. And one of the things I always like to say when I start Chem 106, or second semester general chemistry, is welcome to your first day of college level chemistry, because when we start the discussion of equilibrium and kinetics, what we're really doing is we're adding shades of gray to everything we introduce as absolutes in first semester. First semester, things are soluble or insoluble. They react or they don't react. They're spontaneous or they're non-spontaneous. And on some level, what all of second semester is about is adding shades of gray. How soluble or insoluble? How reactive or non-reactive? How do we change or shift those equilibria so that we can favor what we want to? And so I think it's really beneficial to start this right out with the way the author begins. Now we arrive at the point where real chemistry begins. Chemical thermodynamics is used to predict whether a mixture of reactants has a spontaneous tendency to change into products, to predict the composition of the reaction mixture at equilibrium, and to predict how that composition will be modified by changing the conditions. Although reactions in industry are rarely allowed to reach equilibrium, knowing whether equilibrium lies in favor of reactants or products under certain conditions is a good indication of feasibility of a process. Much the same is true of biochemical reactions, where the avoidance of equilibrium is life, and the attainment of equilibrium is death. This is also a topic we discuss in biochemistry called negentropy, where we are resisting equilibrium processes through the active consumption of energy, and that's an inherent property of life. But that's for a different discussion and a different chapter in a different class. There's one word of warning that is essential to remember. Thermodynamics is silent about rates of reaction. All it can do is identify whether a particular reaction mixture has a tendency to form products. It cannot say whether or not that tendency will ever be realized, and it's chapters 10 and 11 that explore what determines the rate of chemical reaction. Please remember, and I'm going to do a little doodle here, if I can, that if we have this oversimplified reaction chart where we have our reactant starting here and our transition state here and our product here, with energy being on the y-axis and x-axis being reaction progress, that if we were to draw a line indicating our energy of our reactants, that it's the delta in energy between the reactant and the products which determine your equilibrium process, how favorable something is, absolutely regardless of rate. And it's the delta between the transition state and your reactants which determines the rate of reaction. So you have two independent deltas, differences in energy, which will dictate these two independent quantities, equilibrium and rate. So for this chapter, remember, we are all about equilibrium. So the thermodynamic criteria for spontaneous change at constant temperature and pressure is delta G must be less than 0. The principal idea behind this chapter, therefore, is that at constant temperature and pressure, a reaction mixture tends to adjust its composition until its Gibbs energy is a minimum, meaning the reactant is at its most stable state. If the Gibbs energy of a mixture varies, as shown in figure 7.1a, which we'll show shortly, very little of the reactants convert into products before Gibbs energy has reached its minimum value and the reaction does not go. If G varies as shown in figure 7.1c, then a high proportion of products must form before G reaches its minimum and the reaction goes. In many cases, the equilibrium mixture contains almost no reactants or almost no products. Many reactions have a Gibbs energy that varies, also shown in this figure, which we will see on the next slide. And at equilibrium, the reaction mixture contains substantial amounts of both reactants and products. One of our tasks is to see how to use thermodynamic data attempt to predict the equilibrium composition and to see how composition depends on conditions. So, right out the gate with figure 7, or 7.1, to keep our ideas in focus, or focusing on reaction Gibbs energy, we consider two important reactions. One is the isomerism of glucose 6-phosphate, or G6P, to fructose 6-phosphate, F6P, which is an early step in anaerobic breakdown of glucose. And here we can see we have our glucose 6-phosphate and our fructose 6-phosphate, and all we're doing is rearranging these compounds to go from a 6-membered ring to a 5-membered ring. And as we go towards the 5-membered ring, we're trying to develop a pseudo line of symmetry so that we can cleave it into a pair of trioses following a subsequent phosphorylation. But that's your biochemistry too. This reaction takes place in the aqueous environment of the cells. The second is the synthesis of ammonia, which is of crucial importance for industry and agriculture. So for the synthesis of ammonia, you can see that we have nitrogen gas plus 3 equivalents of hydrogen gas yield 2 equivalents of ammonia gas. These two reactions are specific examples of a general reaction in the form of A equivalents of A plus B equivalents of B react in equilibrium reversibly to form C equivalents of C plus D equivalents of D. This is our classic indication of a generic reaction of equilibrium, which we introduce in general chemistry. And of course, we have arbitrary physical states associated with these. First, let's look at reaction A. Suppose that in short interval, while the reaction is in progress, the amount of glucose 6-phosphate changes by delta N moles. As a result of this change in the amount, the contribution of glucose 6-phosphate to the total Gibbs energy of the system changes by the corresponding amount of change to moles, where the chemical potential of glucose 6-phosphate, or the partial molar Gibbs energy of glucose 6-phosphate in the reaction mixture, is being altered because of that decrease. In the same interval, the amount of fructose 6-phosphate changes by positive change of moles. So its contribution to the Gibbs energy changes by a positive chemical potential times the number of moles, or molar chemical potential by the number of moles, where the chemical potential of fructose 6-phosphate is indicated by this term. Provided delta N, or a change of moles, is small enough to leave the composition virtually unchanged, meaning it's a very small incremental change, the net change in Gibbs energy of the system is as follows, where the change in Gibbs energy is going to be the difference between the two quantities we've described, where the molar quantity of glucose 6-phosphate decreases, the molar quantity of fructose 6-phosphate increases, and the delta is going to be determined by their relative change of mole fraction times their molar chemical potential. If we divide through, of course, by delta N, we can obtain the reaction Gibbs energy, or Gibbs energy of reaction, which we see here, where the Gibbs energy of reaction is going to be delta G divided by the change in moles. There are two ways to interpret delta G reaction. First, it is the difference between the chemical potentials of the products and the reactants at the composition of the reaction mixture. Second, because delta G reaction is the change in G divided by the change in composition, we can think of delta GR as being the slope of the graph of G plotted against the changing composition of the system, which is what we're seeing in figure 7.2. So in 7.2, you can see on the x-axis we have Gibbs energy. On the y-axis we have Gibbs energy. On the x-axis we have composition, which ranges from pure reactants on the far left to pure products on the far right. And you can see as we have changes in slope indicated by the green line, we can approximate that slope, since we don't have the equation for tangent, with delta G over the range of the green line divided by delta N over the range of the green line. And therefore we can get delta G R, or delta G of the reaction, over that specific range of composition. So, for the second reaction, the synthesis of ammonia provides a slightly more complicated example. If the amount of nitrogen gas changes by negative delta N, then from the reaction stoichiometry, we know that the change in the amount of hydrogen gas will be negative 3 delta N, and the change in the amount of ammonia gas will be positive 2 delta N. Each change contributes to the change in the total Gibbs energy of the mixture, and the overall change is therefore defined by the following. And really the only difference between this is we have to adjust for the stoichiometry of the reaction, where the chemical potential for some species J are the chemical potentials of the species in the reaction mixture. In this case, therefore, the reaction Gibbs energy is as follows, which is, like I said, very similar to what we saw before. We're just accounting for the Gibbs energy contribution of all three chemical constituents of this equilibrium process. Note that each chemical potential is multiplied by the corresponding stoichiometric coefficient, and that reactants are subtracted from products, like we would always see in every delta process. For the general reaction C, we can generalize the following, where we see that for A units of A plus B units of B, well, I'll write it here, are in equilibrium reversibly with C units of C plus D units of D. We can approximate the change in Gibbs energy for the reaction, or delta GR, for this reaction with 7,1C. The chemical potential of a substance depends on the composition of the mixture in which it's present, and is high when its concentration or partial pressure is high. Therefore, delta GR changes as the composition changes, is what we're seeing in figure 7.3. Remember that delta GR is the slope of G plotted against composition. We see that delta GR is less than 0, and the slope of G is negative, going down from left to right, when the mixture is rich in reactants A and B, because the chemical potential of A and chemical potential of B are then high. Conversely, delta GR is greater than 0 and the slope of G is positive when the mixture is rich in the products C and D, because the chemical potentials for C and D are then proportionally high. As compositions corresponding to delta GR are less than 0, the reaction tends to form more products. As composition corresponds to delta GR greater than 0, the reverse reaction is spontaneous, and the products tend to decompose into reactants. Where delta GR equals 0, at the minimum of the graph, where the slope is 0, the reaction has no tendency to form either products or reactants. In other words, the reaction's at equilibrium. This is the criteria for chemical equilibrium at constant temperature and pressure. Delta GR equals 0. So let's take a look at figure 7.3 here. On the y-axis, we have Gibbs free energy. On the x-axis, we have composition, starting with the far left, pure reactants, and on the far right, pure products. At the minimum of the curve, corresponding to equilibrium, delta GR equals 0, because the slope of the line is 0 at that point. To the left of the minimum, delta GR is less than 0, or is negative, and the forward reaction is therefore spontaneous. And to the right of the minimum, delta GR is greater than 0, and the reverse reaction is spontaneous. So, with that, let's dive in to section 7.2, the variation of delta G for reaction with composition. Our next step is to find out how delta GR varies with the composition of the system. Once we know that, we'll be able to identify the composition corresponding to delta G equals 0. Our starting point is a general expression for the composition, dependence, and chemical potential derived in section 6.5, which is listed here, where A sub j is the activity of species J. When we're dealing with ideal systems, which will be the case in this chapter, we're not going to deal with non-ideal situations here, we use the identifications given in table 6.2, where for solutes in an ideal solution, A sub j equals J over C, the molar concentration of J relative to the standard value C equals 1 mole per decimeter cubed. For perfect gases, A sub j equals P sub j over P, the partial pressure of J relative to the standard pressure, where pressure equals 1 bar. And for pure solids and liquids, A sub j just equals 1. As in chapter 6, to simplify the appearance of expressions in what follows, we shall not write C and P explicitly. So the way to do this is substitution of equation 7.3 into 7.1c gives the following. And that simplifies to what we see here. Note this is for the general reaction of A units of A plus B units of B reversibly react to form C units of C plus D units of D. So not particularly complicated, just a bunch of terms and their corresponding chemical potentials. The first term on the right in the second equality is the standard reaction Gibbs energy. Because the standard state refers to pure materials, the standard chemical potentials in this expression are the standard molar Gibbs energy of the pure species. Therefore, equation 7.4a is the same as the following, where the standard reaction Gibbs energy equals the following. We shall consider this important quantity in more detail shortly. At this stage, therefore, we know that delta GR equals delta GR plus RT times the expression highlighted here. And the expression for delta GR is beginning to look much simpler. To make further progress, we rearrange the remaining terms on the right as follows, and at this point, once you follow the rearrangement, we can conclude that the following, where delta GR is going to equal delta GR under standard conditions modified by the following term, RT natural log A C sub C A D sub D A sub A B sub B. Also remember, A, B, C, and D correspond to the generic equation, which I've written down in the bottom right corner. To simplify this even further, the appearance of the expression specifically, we introduce the dimensionless reaction quotient Q for the reaction C, where Q simply equals the relationship which the natural log is taken of. And note that Q has the form of products divided by reactants, which is very, very similar to what you saw in developing equilibrium constants in 100-level chemistry. But remember that Q, in this particular case, describes not the conditions of equilibrium, but the conditions of the ratio of the reactants over the products raised to their respective coefficients at any particular point in the reaction, and you can compare that to the equilibrium constant and determine whether it moves forward or backward. Now, note that Q has the form of products divided by reactants with the activity of each species raised to a power equal to its stoichiometric coefficient in the reaction. We can now write the overall expression for the reaction, Gibbs energy at any composition, as follows, where it's exactly as written before, except we're now just substituting Q for the reactant over products ratio. This simple but hugely important equation will occur several times in different disguises. So, moving along to 7.3, reactions at equilibrium. When the reaction has reached equilibrium, the composition has no further tendency to change because delta G for the reaction is 0, and the reaction is spontaneous in neither direction. At equilibrium, the reaction quotient has a certain value called equilibrium constant K, which I just referred to in our discussion of Q, and which you've been introduced to in 100-level chemistry. Naturally, this is big K, capital K, by the way. There will be situations where we'll have lowercase k's, which mean different things. So capital K, equilibrium, and that is K equals the ratio of products over ratio of reactants. Now, I keep saying this, but let me break this down in a fashion that you may have seen before. For A of A plus B of B in equilibrium with, that's supposed to be a B, C of C plus D of D, K is going to equal, and you've probably seen it drawn like this, where you have the concentration of C raised to C, concentration of D raised to D, concentration of A raised to A, and B raised to B. This is what you've probably seen as how 7.7 has been illustrated previously. And I just want you guys to have some familiarity with this, but it's the same thing, fundamentally the same thing. It's K. So we'll not normally write equilibrium. The context will always make it clear whether Q refers to an arbitrary stage of reaction, because Q is the same ratio of reactants to products adjusted for stoichiometric coefficients, but it refers to any arbitrary stage in the reaction, including equilibrium, whereas K, the value of Q at equilibrium, specifically is calculated from equilibrium constant composition. So it now follows from equation 7.6 that at equilibrium, the following, because at equilibrium, delta G is 0. So we can say 0 equals delta GR under standard conditions plus RT natural log K, because Q can now substitute for K because it is just simply Q at equilibrium. And therefore, we can rearrange to a potentially comfortable equation that you've seen in 100-level chemistry, where delta G reaction equals negative RT natural log K. This is one of the most important equations in the entirety of chemical equations. Its principal use is to predict the value of the equilibrium constant of any reaction from tables of thermodynamic data like those in the data section. Alternatively, we can use it to determine delta G by measuring equilibrium constants of a reaction over a range of temperatures. So, very important. Delta G equals negative RT natural log K. That means R is a constant, ideal gas law constant. For any specific temperature, we can equate the equilibrium constant, which is the ratio of products over reactants adjusted for the stoichiometric coefficients at equilibrium, to delta G. So we can go back and forth between these terms effortlessly at any given temperature. So, an important feature of this equation, 7.8, is that it tells us that if K is greater than 1, then delta G is less than 0, or is negative. Broadly speaking, if K is greater than 1, that implies that products are dominant at equilibrium. So we can conclude that a reaction is thermodynamically feasible if delta G is less than 0 or negative. Reactions for which delta G are less than 0 are called exergonic. Conversely, because equation 7.8 tells us that if K is less than 1, delta G is greater than 0, then we know that the reaction will be dominant, the reactants will be dominant in a reaction mixture at equilibrium. In other words, a reaction with delta G greater than 0 is not thermodynamically feasible. Reactions for which delta G are greater than 0 are called endergonic. Some care must be exercised with these rules, however, because the products will be significantly more abundant than reactants only if K is significantly greater than 1, like more than about 1,000-fold. And even a reaction with K less than 1 may have a reasonable abundance of products at equilibrium if it's close to 1. And this is particularly true for biochemical processes in metabolism. So let's take a look at figure 7.4 quickly here. The relation between standard reaction Gibbs energy and the equilibrium constant of the reaction, where the pale curve is magnified by a factor of 10. So on the y-axis we have equilibrium constant, and on the x-axis we have standard reaction Gibbs energy. And you can see that these two are easily relatable through the combination of the ideal gas law constant, any specific temperature, and natural log transformation. In fact, if you do an anti-log to this, you can linearize the process and derive delta G experimentally by measuring K over a range of temperatures, which is something we almost always do in General Chem 2 laboratory. So, Table 7.1 summarizes the conditions below under which delta G is less than 0 and K is greater than 1. Because delta G for reaction equals delta H minus T delta S, which we saw previously, the standard reaction Gibbs energy is certainly negative if both delta H is less than 0, exothermic reaction, and delta S is greater than 0, reaction system that becomes more disordered, such as forming a gas. The standard reaction Gibbs energy is also negative if the reaction is endothermic and T delta S is sufficiently large and positive. Note that for an endothermic reaction to have delta G be less than 0, its standard reaction entropy must inherently be positive. Moreover, the temperature must be high enough so that T delta S can be greater than delta H, which is why we have temperature thresholds for spontaneity in endergonic reactions like the melting of ice, which we've discussed in previous chapters. The switch of delta G from positive to negative, corresponding to the switch from K being less than 1, meaning the reaction does not go, to K being greater than 1, the reaction goes, occurs at a temperature given by equating delta H minus T delta S to 0, which is at equilibrium. So we have temperature at which they switch is delta H over delta S. And we can actually see this visually in figure 7.5, where an endothermic reaction may have K greater than 1 provided the temperature is high enough for T delta S to be large enough that when subtracted from delta H, the result is negative. And you can actually see the intersecting temperature effects here, where delta H, T delta S pass each other, and actually that's where this is the point of spontaneity. So, moving right through the chapter, section 7.4, standard reaction Gibbs energy. The standard reaction Gibbs energy, delta GR, is central to the discussion of chemical equilibria and the calculation of equilibrium constants. We've seen that it is defined as the difference in standard molar Gibbs energy of the products and the reactants weighed by their stoichiometric coefficients, V, in the chemical equation 7.10 below, where delta GR equals the sum of G for the products and the sum of G for the reactants. For example, the standard reaction Gibbs energy for reaction A is the difference between the molar Gibbs energy of fructose 6-phosphate and glucose 6-phosphate in solution at 1 mole per decimeter cubed and 1 bar. We cannot calculate delta GR from the standard molar Gibbs energies themselves because these quantities aren't known. One practical approach is to calculate the standard reaction enthalpy from standard enthalpies of formation, which we saw in section 3.5. The standard reaction entropy from third law entropies, which we saw in 4.6, and then to combine the two quantities by using delta G equals delta H minus T delta S. And there's a nice illustration of this below. If you want to move through it, just pause the video and move through this calculation illustration. Now, if you've moved through that example, we saw in section 3.5 how to use standard enthalpies of formation of a substance to calculate standard reaction enthalpies. We can use the same technique for standard reaction Gibbs energies. To do so, we list the standard Gibbs energy of formation, delta G, F, of a substance, which is the standard reaction Gibbs energy per mole of species for formation from the elements in their reference states. The concept of reference state was introduced in 3.5. The temperature is arbitrary, but we shall almost always take it to be 25 degrees Celsius or 298 Kelvin. For example, the standard Gibbs energy of formation of liquid water, delta G, water liquid, is the standard reaction Gibbs energy for the reaction of equivalent of hydrogen gas plus half an equivalent of oxygen gas yields 1 equivalent of liquid water. And it is negative 237 kilojoules per mole at 298 Kelvin. Some standard Gibbs energies of formation are listed on table 7.2 to the right, and more can be found in the data section of the text. It follows from the definition that the standard Gibbs energy of formation of an element in its reference state is 0 because reactions such as carbon solid in this graphite phase converting to carbon solid in graphite phase are null. That is, nothing happens. The standard Gibbs energy of formation of an element in a phase difference from its reference state is non-zero. So in this case, carbon in graphite phase going to carbon in diamond phase has a delta G of positive 2.90 kilojoules per mole. Many of the values in the tables have been compiled by combining the standard enthalpy of formation of the species with the standard entropies of the compound and the elements, as illustrated above, but there are some other sources of data, and we encounter some of them later. Standard Gibbs energies of formation can be combined to obtain the standard Gibbs energy of almost any reaction. We use the now familiar expression, delta G equals the sum V delta G of products minus the sum of V delta G reactants that we see here. Standard Gibbs energies of formation of compounds have their own significance as well as being useful in calculations of K. They are a measure of the thermodynamic altitude of a compound above or below sea level of stability represented by elements in reference states. If the standard, and this is, we should actually jump into figure 7.6 to make sense of that analogy. So in 7.6, you see on the y-axis standard Gibbs energy of formation, and you have these different energy levels for different contributing components. And of course, you have your 0 point, which is your sea level, meaning altitude being your reference in that analogy, where the standard Gibbs energy of formation of a compound is like a measure of the compound's altitude above or below sea level. Compounds that lie above sea level have spontaneous tendency to decompose into the elements and to revert to sea level. Compounds that lie below sea level are stable with respect to decomposition into the elements. The numeric values are, in this particular case, kilojoules per mole. So, having sorted out that analogy, if the standard Gibbs energy of formation is positive, and the compound lies above sea level, then the compound has a spontaneous tendency to sink towards thermodynamic sea level and decompose into elements. That is, if K is less than 1 for the formation of reaction, for their formation reaction, we say that a compound with delta G is greater than 0, it is thermodynamically unstable with respect to its elements, or that is an endergonic compound. Thus, a good example, ozone, for which delta G formation is positive 163 kilojoules per mole, has a spontaneous tendency to decompose into oxygen under standard conditions at 25 degrees Celsius. And more precisely, equilibrium constant for the reaction 1.5 equivalents of oxygen gas is in equilibrium with 1 equivalent of ozone is less than 1, much less in fact, where K is 2.7 times 10 to the negative 29th. However, although ozone is thermodynamically unstable, it can survive if the reactions that convert it into oxygen are slow. That is the case for the upper atmosphere, and ozone molecules, O3, in the ozone layer survive for long periods. Benzene, which has delta G formation of plus 124 kilojoules per mole, is also thermodynamically unstable with respect to its elements. However, the fact that bottles of benzene are everyday laboratory commodities also reminds us that the point made at the start of the chapter, that spontaneity is a thermodynamic tendency that might not be realized at a significant rate in practice. So, always have to understand both sides of the coin to understand the totality of chemical reaction. Another useful point that can be made about standard Gibbs energies of formation is that there is no point in searching for direct syntheses of thermodynamically unstable compounds from its elements under standard conditions as the temperature to which the data apply, because the reaction does not occur in the required direction. The reverse direction, or decomposition, is spontaneous. Endergonic compounds must be synthesized by alternative routes or under conditions for which Gibbs energy of formation is negative and they lie beneath the thermodynamic sea level. So, compounds with delta G formation that are less than 0, which corresponds to K being greater than 1 for the formation of reactions, are said to be thermodynamically stable with respect to their elements, or called exergonic compounds. Exergonic compounds lie below the thermodynamic sea level of the elements. An example is the exergonic compound ethane, where delta G formation is negative 33 kilojoules per mole. The negative sign shows that the formation of ethane gas is spontaneous in the sense that K is greater than 1. In fact, in this case, K is 7.1 times 10 to the 5th at 25 degrees Celsius. So, discussing the equilibrium composition of a reaction. The magnitude of an equilibrium constant is a good qualitative indication of the feasibility of a reaction regardless of whether the system is ideal or not. So broadly speaking, if K is much greater than 1, typically K is greater than 1,000, corresponding to delta G being significantly negative, around the nature of negative 17 kilojoules per mole at 25 degrees Celsius, then the reaction has a strong tendency to form products. If K is much, much lower than 1, or delta G is, so it's about 0.001 or 1/1000th, and delta G is the corresponding positive 17 kilojoules per mole at 25 degrees Celsius, then the equilibrium composition will consist of largely unchanged reactants. If K is comparable to 1, typically lying between 10 to the negative 3 and 10 to the 3rd, then significant amounts of both reactants and products will be present at equilibrium. An equilibrium constant expresses the composition of an equilibrium mixture as a ratio of products of activities. Even if we confine our attention to ideal system, it is still necessary to do some work to extract the actual equilibrium concentrations or partial pressures of the reactants and products given their initial values. In more complicated cases, it's best to organize the necessary work into a systematic procedure resembling a spreadsheet by constructing a table with columns headed by the species and in successive rows. So you need 3 things. 1, the initial molar concentration of solutes or partial pressures of gases. 2, the changes in these quantities that must take place for the system to reach equilibrium, which can be known or unknown. And 3, the resulting equilibrium values. In most cases, we do not know the change that must occur for the system to reach equilibrium. So the change in the concentration or partial pressures of one species is written as x, and the reaction stoichiometry is used to write the corresponding changes of the other species. When the values at equilibrium are substituted in the expression for the equilibrium constants, we obtain an equation for x in terms of k. This equation can be solved for x, and hence the concentration of all species at equilibrium may be found. And this should be really familiar because in Chem 106, Gen Chem 2, you did chapter after chapter after chapter of ice tables, initial change and equilibrium table, ice table. And this is exactly the process which is being described right now. So, because I believe you have an inherent comfort with this or have an experience base, I'm not going to go through this detailed example. However, feel free to pause and run through the example on your own. And if it should be familiar, maybe you just need to knock the dust off of it. Regardless, go ahead and pause the video, run through the example, and then pick it up on the next slide. And the same goes for this example. Give it a shot. See if this makes sense. And if you find that this is struggling for you, talk to me, because I can give you some resources around ice tables to help you review some Gen Chem. But this should be in everyone's wheelhouse, even if it's not something you're inherently comfortable with, because it's probably been 2, 3, maybe even 4 years since you've seen this content. And now that you've had a chance to review ice tables and equilibrium concentrations or deltas, let's keep moving along and start discussing briefly the equilibrium constant in terms of concentration. So, an important point to appreciate is that the equilibrium constant K calculated from thermodynamic data refers to activities. For gas phase reactions, that means partial pressures, explicitly Pj over P. This requirement is sometimes emphasized by writing K as K sub P, but the practice is unnecessary if the thermodynamic origin of K is remembered. In practical applications, however, we might wish to discuss gas phase reactions in terms of molar concentrations. The equilibrium constant is then denoted K sub C, with C being concentration, and for a reaction B, with synthesis of ammonia, it looks like this, where K based on concentrations is going to be equal to the product, ammonia's concentration, raised to its stoichiometric coefficient of 2, divided by the product of nitrogen concentration to the first power and hydrogen's concentration to the third power. So for this reaction B, which we're seeing, the molar concentration J is interpreted as J over C, where C is equal 1 mole per decimeter. To obtain the value of K sub C from thermodynamic data, we must first calculate K and then convert K to Kc by using, as shown, the derivation in the text 7.1, this relationship. Which is simply relating K to K sub C with an adjustment factor, taking into account temperature, ideal gas law, pressure, and change of volume of the gas. In this expression, this delta V gas is the difference in the stoichiometric coefficients of the gas phase species products minus reactants. We get a very convenient form of this expression by substituting the values of C, P, and R, which give us 713b, which is much more workable. And there's a nice illustration of how to use this here. I don't think anyone's going to struggle to solve that one. So, the response of equilibria to conditions of reaction. In introductory chemistry, we learned the empirical rule of thumb known as Le Chatelier's principle. When a system at equilibrium is subjected to a disturbance, the composition of the system adjusts so as to tend to minimize the effect of that disturbance. For example, if a system is compressed, then the equilibrium position can be expected to shift in a direction that leads to the reduction of the number of molecules in the gas phase, for that tends to minimize the effect of the compression. Le Chatelier's principle, though, is only a rule of thumb, and to understand why reactions respond as they do, and to calculate the new equilibrium composition, we need to use thermodynamics. We need to keep in mind that some changes in conditions affect the value of delta GR, and therefore K. Temperature is the only instance where others change the consequences of K having a particular fixed value without changing the value of K, for instance, pressure. Now, one quick note on catalysts. A catalyst is a substance that accelerates a reaction without itself appearing in the overall chemical equation, meaning it's not consumed as part of the reaction. Enzymes are biological versions of catalysts, essential for living processes, and we study the action of catalysts in section 10.12, and at this stage don't need to know the details of how they work, other than they provide an alternative, faster route from product to reactant, or reactant to product. Although the new route of the reactant to product is faster, the initial reactants and the final products are exactly the same. And therefore, the quantity delta GR is defined as the difference between the standard Gibbs-Muller energy of reactants and products, so it's independent of the path linking the two. It follows that an alternative pathway between reactants and products leaves delta G, and therefore K, unchanged. So the presence of a catalyst does not change equilibrium constant of a reaction. Incredibly important. A catalyst won't make an unfavorable reaction favorable. It will simply accelerate the rate of reaction, regardless of whether it's favorable or unfavorable. Now, let's talk about the effects of temperature. According to Le Chatelier's principle, we can expect a reaction to respond to a lowering of temperature by releasing heat, and to respond to an increasing of temperature by absorbing heat. That is, when the temperature is raised, the equilibrium composition of an exothermic reaction will tend to shift towards reactants, and the equilibrium composition of an endothermic reaction will tend to shift towards products. In each case, the response tends to minimize the effect of raising the temperature. But why do reactions at equilibrium respond in this way? Le Chatelier's principle is only a rule of thumb and gives no clue as to the reason for this behavior. As we'll see now, the origin of this effect is the dependence of delta GR, and therefore K, on temperature. So, first, we consider the effect of temperature on delta G. We use the relationship delta G equals delta H minus T delta S and make the assumption that neither the reaction enthalpy nor the reaction entropy varies much with temperature over small ranges at least. It follows that change in delta G equals the change in T times delta S. This expression is easy to apply when there is a consumption or formation of gas because, as we have seen, gas formation dominates the sign of the reaction entropy. So, now consider the effect of temperature on K itself. At first, this problem looks troublesome because both T and delta G appear in the expression for K. However, as shown in derivation 7.2 in the text, if you're interested to go in looking at the derivation, the effect of temperature can be expressed very simply by the Van't Hoff equation, where K is the equilibrium constant at the temperature T, and K prime is the value when the temperature is T prime. All we need to know to calculate the temperature dependence of an equilibrium constant, therefore, is the standard reaction enthalpy. Incredibly useful reaction. So, looking at figure 7.7 before moving along, the variation of reaction Gibbs energies with temperature dependence on the reaction entropy and therefore on the net production or consumption of gas in a reaction, as indicated by the blue boxes, which shows the relative amounts of gas on each side of the equation. The Gibbs energy of a reaction that produces gas decreases with increasing temperature. Gibbs energy of a reaction that results in a net consumption of gas increases with temperature because of the impacts on entropy. So, let's talk a little bit about coupled reactions and biochemical processes, and then we'll hop back in to where we're going. A reaction that is not spontaneous may be driven forward by coupling it to a reaction that's spontaneous. A simple mechanical analogy is a pair of weights joined by a string in the illustration below. The lighter of the pair of weights will be pulled up as the heavier weight falls. Although the lighter weight has a natural tendency to move downward, its coupling to the heavier weight results in it being raised. The thermodynamic analog is an endergonic reaction, the analog of the lighter weight, being forced to occur by coupling it to an exergonic reaction, the analog of the heavier weight falling to the ground. The overall reaction is spontaneous because the sum of delta G for the two half reactions is negative. The whole of life's activities depend on couplings of this kind, for the oxidation reactions of food act as the heavy weights that drive other reactions forward and result in the formation of proteins from amino acids, the actions of muscles for propulsion, and especially the activities of the brain for reflection, learning, and imagination. In fact, fun fact, at rest, your brain consumes about 90% of your oxygen because it takes an enormous amount of energy to establish and maintain the gradients which allow for neuronal communication and function and potentiation. So, having said that, let's explore the information in the Van Hoff equation. Consider the case where, and let's do a quick reminder. There we go. Consider the case where t prime is greater than t, over here. Then the term in the parentheses is positive. If delta H is greater than 0, corresponding to an endothermic reaction, the entire term on the right is positive. In this case, therefore, natural log of k prime is going to be greater than natural log of k. That being so, we conclude that if k prime is greater than k for an endothermic reaction. In general, the equilibrium constant of an endothermic reaction increases with temperature. The opposite is true if delta H is less than 0. So we conclude that the equilibrium constant for an exothermic reaction decreases with an increase in temperature. Makes sense. Less motivation for it to move forward or for it to go backward. The conclusions we have outlined are of considerable commercial and environmental significance. For example, the synthesis of ammonia is exothermic, so its equilibrium constant decreases as the temperature is increased. In fact, K falls below 1 when the temperature is raised above 200 Celsius. Unfortunately, the reaction is slow at low temperatures and is commercially feasible only if the temperature exceeds about 750 Celsius, even in the presence of a catalyst. But then K is very small. We'll see shortly how Fritz Haber, the inventor of the Haber process for the commercial synthesis of ammonia, was able to overcome this difficulty. Another example is the oxidation of nitrogen, where you have nitrogen plus oxygen leads to nitrogen monoxide, two equivalents of nitrogen monoxide. This reaction is endothermic, with a delta H of positive 180 kilojoules per mole, largely as a consequence of the very high bond enthalpy of nitrogen, so its equilibrium constant increases with temperature. It is for this reason that nitrogen monoxide is formed in significant quantities in hot exhausts of jet engines and in the hot exhaust manifolds of internal combustion engines, and then goes on to contribute to the problems caused by acid rain. A final point in this connection is that to use the Van Hoff equation for the temperature dependence of Kc, we first convert Kc to K by using equation 713 at the temperature at which it applies. and use equation 715 to convert K to the new temperature, and then use equation 713 again, but with the new temperature to convert new K to Kc. As you might appreciate, on the whole, it's just better to stick to using K instead of K sub C. So we talked about temperature. Let's talk about compression. We've seen that Le Chatelier's principle suggests that the effect of compression, decrease in volume, on a gas phase reaction at equilibrium is as follows. When a system at equilibrium is compressed, the composition of a gas phase equilibrium adjusts so as to reduce the number of molecules in the gas phase. For example, in the synthesis of ammonia, reaction B, 4 reactant molecules are give 2 product molecules, because we have a 1 plus 3 goes to 2. Indeed, this is the key to resolving Haber's dilemma, for by working with high compressed gases, he was able to increase the yield of ammonia. Pressure plays an important role in governing the uptake and release of oxygen from oxygen transport and storage proteins, which we'll talk about in box 7.2 shortly. Let's explore the thermodynamic basis of this dependence. First, we note that delta GR is defined by the difference between Gibbs energies of substances and their standard states, and therefore 1 bar. It follows that delta G has the same value whether the actual pressure used for the whatever the actual pressure used for the reaction. Therefore, because natural log of K is proportional to delta G, K is independent of the pressure at which the reaction is carried out. Therefore, if the reaction mixture in which ammonia is being synthesized is compressed isothermally, the equilibrium constant remains unchanged. This rather startling conclusion should not be misinterpreted. The value of K is independent of pressure to which the system is subjected, but because partial pressure occurs in the expression of K in a rather complicated way, that does not mean that the individual partial pressures or concentrations are unchanged. Suppose, for example, the volume of reaction vessel in which the reaction of hydrogen plus iodine is equilibrium with 2 equivalents of hydrogen iodide gas has reached equilibrium is reduced by a factor of 2, and the system is allowed to reach equilibrium again. If the partial pressures were simply to double, that is, there's no adjustment of composition by further reaction, the equilibrium constant would change from this term, K, to this term, K prime, where everything's multiplied by 2. However, we've seen that the compression leaves K unchanged. Therefore, the 2 partial pressures must adjust by different amounts. In this instance, K prime will remain equal to K if partial pressures of HI change by a factor of less than 2, and the partial pressures of H2 increase by more than a factor of 2. In other words, the equilibrium constant composition must shift in the direction of the reactants in order to preserve the equilibrium constant. Everything tries to maintain the equilibrium constant, and the ratios of reactants to products shift to try to maintain that value. We can express this effect quantitatively by expressing the partial pressures in terms of the mole fractions and the total pressure. For the reaction above, we find the following, where we just multiply by mole fractions. For K to remain constant at the pressure is increased, the ratio of mole fractions must decrease, implying that the proportion of hydroiodic acid in the mixture must increase. Because the mole fraction of hydroiodic acid plus hydrogen must equal 1, the explicit dependence of the mole fractions can be found by substituting mole fraction of hydrogen equals 1 minus mole fraction of hydroiodic acid, which gives the following. So now we have a single variable for hydroiodic acid, and solving the resulting quadratic equation gives you the following. Because a mole fraction must be positive, inherently you can select the following solution. The dependence of the mole fraction implies by this expression is shown in figure 7.8. Note that as pressure becomes 0, the mole fraction of hydroiodic acid approaches 1. This limit's derived in derivation 7.3 if you're interested in pursuing that derivation in the text. So let's take a look at 7.8. On the x-axis we have mole fraction of hydroiodic acid, and on the x-axis we have the total pressure. And you can see the mole fraction of hydroiodic acid molecules in a gas phase reaction mixture of H2 and HI as a function of pressure. The I2 is present as a solid throughout, so it's excluded from these because it doesn't have contributing pressure. And that is going to be it for the introduction of new principles for the chapter. But before we go, one last slide. I want everyone to take a look at the binding of oxygen to myoglobin and hemoglobin because it's one of our classic cases, and it's particularly interesting because of the complexity of allosteric regulation associated with it. For those of you who've had biochemistry, you've heard of that. If you haven't had biochemistry, you'll hear about it in the future. However, the protein myoglobin stores oxygen in muscle, and the protein hemoglobin transport oxygen in blood. Hemoglobin is composed of 4 myoglobin-like molecules. In each protein, the oxygen molecule attaches to an iron in the heme group, and each myoglobin-like component of hemoglobin responds to the change in shape of others when oxygen binds to them. So as oxygen binds, it actually modifies the structure of the heme groups and globins to alter the way in which it's binding the oxygen, how strongly that is. So first, consider the equilibrium between myoglobin and oxygen, where aqueous myoglobin plus oxygen as separate quantities are in equilibrium with myoglobin bound to oxygen. And this can be expressed as a K term here, where P is the numeric value of the partial pressure in bars of oxygen gas. It follows that the fractional saturation, or S, the fraction of myoglobin molecules that are oxygenated, is as following, where it's the concentration of oxygen in myoglobin over the concentration of total myoglobin. The dependence of this S term, which is our fractional saturation, on the partial pressure is shown in the following illustration, where you can see for myoglobin in green, it shoots up quickly and then levels off, and for hemoglobin, it behaves differently due to its allosteric regulation, where it responds slowly at first and then has a zone of rapid movement and then falls off. And you can see on the x-axis that you have partial pressures of oxygen listed at 50 and 100 and 150, and you see these dotted lines of orange that correspond to the partial pressures of oxygen typical of resting tissues and at the lung. So you can see that you have different partial pressures when the hemoglobin hits the lung versus where it's at resting tissues. And you can also see how much more strongly myoglobin is saturated at both of those areas, but how more similarly they are at the lung. Now consider the equilibrium between hemoglobin and oxygen, where you have 4 different equilibria because it can bind 4 different oxygens. So to develop an expression for this fractional saturation, we express the hemoglobin with 2 oxygens in terms of hemoglobin with single oxygen by using K2, then express HbO2 in terms of Hb by using K1, and likewise for all the other concentrations. What we can take from this entire process is that the binding of oxygen to hemoglobin is an example of cooperative binding, in which the binding of a ligand, in this case oxygen, to a biopolymer, in this case hemoglobin, becomes more favorable thermodynamically, that is, the equilibrium constant increases, as the number of bound ligands increases up to the maximum number of binding sites. We see the effect of cooperativity in the illustration. Unlike myoglobin, which has the saturation curve in green, the hemoglobin saturation curve is sigmoidal. The fractional saturation is small at low ligand concentrations. It increases sharply at intermediate ligand concentrations and then levels off at high levels of ligand concentrations. Cooperative binding of oxygen by hemoglobin is explained by an allosteric effect, in which an adjustment to the conformation of the molecule when one substrate binding affects the ease with which a subsequent substance can bind. The binding of the first changes the structure to increase the affinity for the second, which changes the structure, which increases the affinity again for a third, all the way up. So you have that cooperativity effect based on the allosteric regulation. The differing shapes of the saturation curves for myoglobin and hemoglobin have really important consequences for the way oxygen is made available in the body. In particular, the greater sharpness of hemoglobin saturation curve means that hemoglobin can load oxygen more fully in the lungs and unload it more fully at different regions in the organism. In the lungs, where the partial pressure is about 14 kilopascals, the degree of saturation is about 98%, representing almost complete saturation. In resting muscle tissue, the partial pressure is equivalent to about 5 kilopascals, corresponding to a degree of saturation about 75%, implying that sufficient oxygen is still available should a sudden surge of activity take place. If the local partial pressures fall below 3 pascals, S falls to about 0.1, meaning only 10% saturation, so it will unload its oxygen aggressively. Note that the steepest part of the curve falls in the range of typical tissue oxygen and oxygen partial pressures. Myoglobin, on the other hand, begins to release oxygen only when pressure has fallen below 3 kilopascals. So it acts as a reserve to be drawn on only when hemoglobin oxygen has been nearly completely consumed. So that is all for this chapter. We're going to pick up with one more chapter regarding the specifics of equilibrium, and then we're going to move on to kinetics. So I'll be talking to you about all that shortly.